Hey everyone, and welcome to this explainer. Today we are unlocking something absolutely fascinating, the hidden, microscopic dance of thermodynamics that's literally happening inside the everyday objects all around you. We usually think of metal as something permanent, right? Just hard and unyielding. But before it becomes the solid structures we rely on, it goes through this chaotic, just incredible transformation.
Okay, let's dive right into this. Just take a look at this visually arresting tree of gold rings, produced through what's called investment casting. Casting is actually a really ancient trick. Humanity has been pouring liquid metal into molds since around 4000 BC to make things like ornaments and arrowheads. But as you'll see today, this ancient art is actually governed by some incredibly complex modern science.
Now you might be wondering, why does this matter to me? Well, I want you to picture the car you drive every single day. From the outside, it's this sleek, finished machine. But underneath the hood, it is entirely depending on the bizarre physical transformations we're about to explore.
And this brilliantly illustrates exactly what I mean. If you look at a typical car, you're going to see a massive array of cast parts. The engine block housing the combustion, the brake cylinders and rotors that bring you to a safe stop, the transmission housing, they are all born from liquid metal. Casting doesn't just belong to the Bronze Age, guys. It actively builds our cutting-edge modern world by allowing us to create intricate, complex shapes all in a single piece.
All right, Section 1, from liquid to solid. So, it's super important to understand that molten metals don't just dry like wet paint on a wall. They undergo a profound structural change at the atomic level. Now, the textbook process is simple enough, right? Step 1, pour molten metal into a mold that has a cavity of your desired shape. Step 2, allow it to cool and solidify. And Step 3, remove the newly formed part. Simple. But the magic, and honestly the danger, lies entirely in Step 2.
Moving on to Section 2, the pure metal freeze.
To really grasp that second step, let's look at pure metals. Just like water turns to ice at exactly 0 degrees Celsius, pure metals have a highly predictable exact freezing point. Take tungsten, for example. It freezes into a solid at exactly 3410 degrees Celsius. No way around it. When a pure metal hits its specific freezing point, the temperature actually just stays constant for a while. Why? Because as it turns from a liquid to a solid, it gives off something called the latent heat of fusion. The solid front moves uniformly from the cool walls of the mold right into the center.
But here is where a massive headache begins for engineers. As that metal solidifies, it shrinks. And then it continues to shrink as it cools all the way down to room temperature. This physical shrinking act can literally pull the material apart from the inside, causing invisible internal micro-tears, micro-cracking, and porosity. It is a constant, invisible battle against the laws of physics.
Section 3, the alloy mushy zone.
Now, what's really interesting about this slide is the stark contrast when we pivot from pure metals to alloys, which are just mixtures of two or more elements. If you thought pure metals were tricky, check this out. While pure metals freeze instantaneously at one constant temperature, alloys freeze gradually across a whole range of temperatures. They don't just snap from liquid to solid. They enter this strange, weird middle ground. Believe it or not, engineers actually call this middle ground the mushy zone. I know, it's a funny, highly memorable thermodynamic term, but it's incredibly serious business. The mushy zone is the temperature range where the alloy is in a pasty state, part liquid, part solid. Ferrous castings like steel have a very narrow mushy zone, but materials like aluminum and magnesium, they have very wide mushy zones, meaning they stay in this pasty, half-melted state throughout almost their entire cooling cycle.
Section 4, microscopic metal trees.
So what is actually floating around inside that mushy zone? Well, to find out, we need to zoom all the way into the microscopic level. Inside the mushy zone, the solidifying metal forms what are called dendrites. The word itself comes from the Greek word dendron, which literally means tree, and honestly, that is exactly what they are. They are tiny, three-dimensional, interlocking metal trees that grow their own branches and secondary arms right inside the liquid mold as the temperature drops. It's like a microscopic forest growing in real time.
Let's look at how these tiny trees organize themselves. On the left here, you can see what happens at the relatively cold mold walls. The metal cools rapidly, forming the skin of fine, equally sized grains. But as you move inward, the grains grow into long columns pointing in the exact opposite direction of the heat transfer. We call these columnar grains. Now on the right, you can see a totally different structure of fine, equiaxed grains uniformly distributed. How these crystalline structures lock together determines the final real-world properties of the metal.
But, as these branches grow, things get pretty messy. The concentration of the alloying elements actually shifts during freezing. The solidifying branches literally push other elements into the remaining liquid.
This causes chemical segregation. You can get microsegregation, where the surface of a tiny dendrite has a totally different chemical makeup than its core. You can even get gravity segregation, where heavier elements physically sink to the bottom of the mold while lighter ones float to the top, before the metal completely freezes.
Which brings us to Section 5, Controlling the Cool.
So, the crucial point is, with elements separating, metal shrinking, and dendrites growing everywhere, how do we make anything useful out of this chaos? Let's zoom back out to the macro level. Why does the size of these microscopic grains actually matter to you and me? Well, it's not just academic. It is absolutely crucial for material safety.
It all comes down to a secret weapon, the cooling rate. If engineers cool the metal slowly, you get coarse grains and huge spaces between the dendritic arms, which basically just leaves room for microscopic voids and weakness. But if you increase the cooling rate, you force the metal to form much finer grains with tightly packed dendritic structures. This fast cooling directly increases the physical strength and ductility of the part and drastically reduces the chance of hot tearing or cracking. It's literally how we ensure that the brake rotors on your car don't just shatter under pressure.
Let's move along and see how this builds into some genuinely mind-bending modern applications, like freeze casting. Instead of fighting dendrite growth, modern engineers actually use it to their advantage. By suspending solid particles in a liquid slurry, like water, and intentionally freezing it, the growing ice dendrites push the solid particles into highly structured patterns. Once you remove the ice, you're left with incredibly complex, highly engineered porous metals or ceramics used in advanced tech. We are literally sculpting with microscopic ice crystals.
From a liquid soup of chaotic atoms to interlocking microscopic forests of metal, the things we interact with every single day are the result of a perfectly timed thermodynamic dance. So I leave you with this thought. If engineers can completely alter the strength and safety of a metal part just by manipulating how quickly these microscopic trees grow, what other invisible, hidden structures are quietly holding your world together today? Thanks for joining me on this explainer, and I hope you never look at a metal object the exact same way again.